So this is the network. In this network, in numerical, it is written that obtain the Norton's equivalent network for this circuit. So this is another one. AC supply is connected. AC voltage source. The value of AC voltage source is 10 at an angle 45 degree. And this is the circuit, and this is the load side terminal between terminal A and B. Here you can see this is the resistance 10 ohm, 5 ohm resistance. The capacitive reactance is minus J2 ohm. This is the resistance. This is the inductive reactance J2 ohm. This is the resistance. Here you can see the minus J2 for the capacitive reactance, plus J2 for inductive reactance. Value may be changed for in any numerical, but plus must be there for inductive reactance and minus must be there for capacitive reactance. So for the Norton's theorem, again the step one is we have to find out the IN. This is Norton's current. So in step one, we will calculate the Norton's current or short circuit current. Both are right. So earlier we have seen that in Thevenin's theorem, uh, step one was we have to find out the Thevenin's voltage or open circuit voltage. So here you have to find out the Norton's current or short circuit current. So this is the primary circuit. So this primary circuit. So to get or to calculate the Norton's current, you just need to short this terminal. You need to short this terminal. Here I have redrawn this circuit. I have just shorted these two terminal, and remaining all part are same as this. Here you can see this part is short, and here I have taken the direction. This is the short high end Norton's current. So again here you can see there is three loop is there or three mesh is there. One this is the one mesh. This is another one mesh, and this is another one mesh. So here I am just pointing out. This is one mesh. Taking another one. This is another one mesh. This is another one mesh, and this is another one mesh. These three mesh. So for the mesh one, I am applying KVL here. So similarly, as discussed earlier, I am applying KVL in this loop or in this mesh one. So here I have taken the direction of current clockwise. For all loop, for this mesh 2 is clockwise I2. For mesh 3, I have taken I3. So first I will calculate the I am applying the KVL at loop or sorry mesh 1. So here minus 2 current is flowing through this. That's why this is the minus, this is the plus. So that's why plus 10 at an angle 45 degree. And in mesh 1, these two are connected in series, 10 minus J2. This is written 10 minus J2. But current flowing through this here from this side to this side. So here the I can see drop in potential. That's why this minus sign. The voltage drop across this here is 10 minus J2 into current flowing through this branch. 10 minus J2 into current flowing through this branch. Here we can see the current I1 is flowing through for this mesh, and similarly current I2 is flowing through this for this mesh. So that's why the difference of the current is I1 minus I2 here written. So total voltage drop across this branch is 10 minus J2 into I1 minus I2, and this minus sign for this drop in potential. Similarly, in mesh 1, the voltage drop across this 5 ohm resistance is 5 into I1 for this mesh, and I3 is also flowing through this resistance. So the total resultant current is flowing through this I1 minus I3. The voltage drop across this is 5 into I1 minus I3. But for this loop, I am doing the for mesh 1. That's why plus 2 minus drop in potential. That's why this minus sign is considered here. Okay. Then we need to solve this equation. 10 at an angle 40 degree minus 10 I1 plus 10 I2 plus J2 I1, then plus minus into minus plus J2 to minus J2 I2, then minus 5 I1 plus 5 I3 is equal to 0. Then solving by simplifying this one, here I am getting minus 10 I1 minus 5 I1, there is a minus 15 I1, then plus J2 I1, I have written plus J2 I1, then plus 10 I2 plus 10 I2, then minus Z2 I2 minus Z2 I2, then plus 5 I3 plus 5 I3 is equal to minus 10 at an angle 45 degree. Again, I am taking this part is common from here. We are taking minus common from here. I am getting here 15 I1 minus of J2 I1 minus 10 I2. Here it will be plus J2 I2 minus 5 I3 is equal to 10 at an angle 45 degree. So here I am combining just I1 part to 15 I1. So I'm taking I1 common. So 15 minus Z2 I1 plus minus 10 plus J2 I2 minus 5 I3 is equal to 10 at an angle 45 degree. So this is the equation 1. Similarly, I have to apply KVL at mesh 2 and mesh 3. So for the mesh 2, what it will be coming? It is coming similarly for this one. Here I have redrawn the circuit. So for the mesh 2, the total voltage drop across this is 10 minus J2. The direction of current towards this. So this is the plus side for this branch only. As the current flowing towards this. So minus of 10 minus Z2 into the current flowing through these branches I2 minus I3. Similarly for this one, and the current flowing through this branch is minus 5 I2 is equal to 0. After simplifying this, again I am getting minus 10 I2 plus 10 I1 plus Z2 I2 minus Z2 I1 minus 5 I2 is equal to 0. Then after solving this, it is coming minus 10 plus Z2 I1 plus 15 minus Z2 I2 is equal to 0. This is the equation 2. Again, we have to apply the KVL at loop 3. Similarly, for this loop 3, here the current is flowing I3 minus I1. This side is plus, this side is minus for the mesh 3. So here I have written 5 into I3 minus 5 into I3 minus I1. But drop in potential minus, that's why this minus sign. And here, here for this branch, current is flowing 10 minus J2. 10 plus J2 because this is the inductance 10 plus J2 into I3, and here similarly current flowing through this, that's why this side is plus, this side is minus 10 K plus 2 I3. So after solving this one, I am getting minus 10 I3 minus J2 I3 minus 5 I3 plus 5 I1 is equal to 0. So simplifying this one, I will be getting minus 5 I1 plus 15 I3 plus J2 I3. And it is coming minus 5 I1 plus 15 plus J2 I3. I am just taking common I3 from these equations. Similarly, as previous, again you need to write these three equations in matrix form. So from equation 1, 15 minus J2 I1 minus 10 plus J2 I2 minus 5 into I3. Similarly, from equation 2, minus 10 plus J2 I1, 15 minus J2 I2, 0 into I3. From equation 3, minus 5 I1, I2 part is not there, that's why I have written 0, and 15 plus Z2 I3. So just here we need to give the all the coefficient of I1, I2, I3. For equation 2, coefficient of I1, I2, I3. For equation 3, from equation 3, coefficient of, this is the coefficient of I1, this is the coefficient of I2, this is the coefficient of I3. And the right hand side part will be written in this side. So we need to calculate the Norton's current. If you see the diagram or this network, the IN is the resultant in between I3 minus I2. That's why we need to calculate I2 current and I3 current. I2 current we can easily calculate it from the Cramer's rule. So the determinant of this is directly written here in denominator part. And here we have to calculate the I2. That's why this right hand part will be placed in the middle. And similarly for the I3, this right hand part will be placed at this third column. The remaining part will be as it is as this. And denominator part will be denominator of this matrix. Here I have drawn. So similarly, as per previous formula, we can solve this one. 15 minus Z2 into this, minus of this into this, then minus of 10 at an angle 40 degree, then minus 10 J2 into 15 plus J2, minus of 0 into minus 5. Then minus 5 into this, minus of this into this. And this is the determinant. In same way, we can solve this denominator also. After solving this, we will be getting 1 at an angle 41.28 degree. Similarly, for the I3, I can get these values. The Norton's current is equal to I3 minus I2. So this is the polar form. So again, you need to convert, or you need to do polar form into a rectangular form. To convert from polar to rectangular, you just do it using A2MS calculator. So for the rectangular, you just press rectangular. To press the rectangular, you just press shift fold. This coming REC rectangular. Then put two values 0.49, comma 37.41. That's close is equal to this. This is coming 0.389. This is the real part. And to get the imaginary part, you just press RCL 10. It is coming J29. Sorry, J.297. So similarly, you have to do this first. And after solving this, you'll be getting this one. Next, in Thevenin's theorem, we have calculated the ZTAs. Similarly, same formula. Here we have to use. Here I have written Zn. That means Norton's equivalent impedance. So to here voltage source was there. The voltage source will be replaced by short circuited. So this is replaced by short circuited. And here I am redrawing the circuit. So 10 minus J2 is parallel with 5. This 10 minus J2 is parallel with 5. This 10 minus J2 is parallel with 5. Then 5 parallel with 10 plus J2 is 5 parallel with 10 plus J2. Just simplified this circuit. So total Norton's equivalent impedance is equal to 5 parallel 10 minus J2 plus 5 parallel 10 plus J2. Here I have written this. So 5 into 10 minus J2 divided by 5 plus 10 minus J2 plus 5 into 10 minus 10 plus J2 divided by 5 plus 10 plus J2. Just solving this, both are in rectangular form. So here I have converted this rectangular form to polar form. Again, this polar form to rectangular form to polar form. For this also, this rectangular form to I have convert polar form. I'm just showing you for this one to convert this 50 plus Z10 to polar from 50.99. Select pole, then value, give to value 15 comma 10 bracket close. It is coming 50.99. Here you can see 50.99. And for the angle, you just press RCL 10. So here you can see RCL 10, 11 point this. So again, this is you just divide these two directly 50.99 divided by 50.13. For this angle, you just press just minus it. That means minus 11.31 degree minus of minus 7.56. And similarly for this one, 50.99 divided by 15.13 and angle will be 11.31 minus 7.59. So it is coming this one. Again, you can see here both are in polar form. So again, you need to convert this polar to rectangular. After converting rectangular to polar, you will be getting this value. For this one, you will be to convert from polar to rectangular, you will be getting this. So you need to add this to real part, add this to real part, and add this to imaginary part. This imaginary part. After this, you will be getting this one. In next Norton's equivalent circuit, here Norton's current, we have derived that this is the Norton's current and this is the IN, this is the IN, and this is the ZN or ZN. So in earlier cases in Thevenin's theorem, the VTH was there, but here IN is there. IN is the current source, Norton's equivalent current source, and this equivalent impedance is parallel with current source. But earlier cases, Thevenin's theorem, the Thevenin's voltage is series with in Thevenin's impedance. But here, current source is parallel with Norton's impedance. So this is the Norton's equivalent circuit. Again, if you have asked to calculate the current flowing through the load resistance, so for this, again you need to add the this load impedance or load resistance in the load terminal earlier, which was removed during the calculation of IN. Actually, not removed. Earlier, it was shortened for the Norton's theorem. So again, need to add this load impedance. So here again, I am drawing the Norton's equivalent circuit. This is the Norton's current source. This is the Norton's impedance. This is the load impedance. So here, by applying the current divider rule, I can easily calculate the load current. So load current is equal to this is the current flowing through this branch. So load current is equal to total current coming at that node. So total current is this one into the parallel branch impedance or opposite side resistance impedance. This is divided by total impedance of this loop. That means 5 plus J2 plus 6.72 plus. Then you solve this.